functions that are linear or nonlinear and be able to try and tell the difference, because that's a really important thing. First of all, let's practice a couple of problems that we've already learned about, just see how we're doing. So the first one says, use the graph to find a linear function that relates y to x. So in this case, we're going to look for the slope, which is m, the y-intercept, which is b, and then write the function of the equation in slope-intercept form. So first of all, if we find the y-intercept, that's where it crosses the y-axis. So that happens to be at 3. And then from that y-intercept, we know if we go down 1 and over 2, that we're back on the line. So down 1 over 2 is the change in y over the change in x. So then our equation would just be y equals negative 1/2 x plus 3. Not too bad, right? Okay, then we discussed whether or not the domain is of a function is discrete or continuous, which means, would it make sense, if we were to graph this data, would it make sense just to put individual dots on the graph, or would we make the dots and then draw a line to connect the dots, because everything in between could also be, and it would make sense for it to be a solution. So let's look. If we notice that we're talking about how much it costs to go to a movie. Well, movie tickets are a fixed price. So one movie ticket costs $9. 2 movie tickets cost $18. So these are fixed prices for individual movie tickets. So it wouldn't make sense to charge you somewhere in between $9 and $18 for 1.5 movie tickets. So in this particular case, this data remains separated. You wouldn't connect it with a line on the graph. So this is what we call discrete data. The next one, we're going to write the following function in, or the following equation in function form, and that means to solve for y and put it into y equals the slope times x plus or minus the y-intercept form. Well, we've done that a few times, so we're going to start by moving the 3x to behind the equal sign, which is where it is in this form. So when we do that, our initial equation will then transform to 2y equals negative 3x, because 3x becomes minus 3x when it crosses the equal sign, and then we have subtract 6. So our next step will be to divide everything by negative 2 so that we can get y alone. So we do that by showing it in this way. Now to finish it off, negative 2 divided by negative 2 is positive 1y. And negative 3 over negative 2, well, it just remains 3 over 2, but the negatives cancel because there's 2 of them. So 3/2 x. And negative 6 divided by negative 2 is positive 3. So this would be our equation in function form, or solved for y. All right, let's move along here then. So today we're going to talk about linear functions and nonlinear functions. And so far we've had graphs, we've had tables of values, and equations. So how can we tell, look at it at any one of those mediums? Well, linear equations is an equation that has a constant rate of change, and the graph is a straight line. So you can tell if a function has a straight line as its graph, it's considered a linear function. If a function has not a straight line, if it's a curvy line, or a U-shaped, or a V-shape, so it does not have a constant rate of change, then the graph is not a straight line. So nonlinear functions are graphs that are not a straight line and don't have a constant rate of change. Not a constant rate of change, not a straight line. Okay, let's see what we mean now. So let's take a look at these tables of values. So let's check out the change in y and the change in x. So in this first one, the change in y on the first step would be minus 8. Change in y on the second step, minus 8. Change in y on the third step, minus 8. That's looking pretty constant so far. How about the top? Change in x plus 3, change in x plus 3, change in x, plus 3. So our slope on this particular one would be negative 8/3, which is a constant rate of change. So this one would be linear, right? Linear. Okay, how about the next one? Let's take a look at the change in y. To go from 2 to 11, that's a change of a positive 9. To go from 11 to 33, that's a change of 22. And to go from 33 to 88, that's a change of 55. That's a massive change. So as you notice, each time we go up a step, these are going up by more each time. In the meantime, we're just going up by 2 each step in the x direction. So each time we go up by 2, the change in y is drastically different. So because of that, this is nonlinear. You couldn't even write a slope for this because each rate of change, or the change in each one, is different. All right, moving right along. Let's check out a few more tables. So we're just going to check the rate of change between the x and the y values. So plus 2 on this side, plus 2, going up by 2. In the y direction, we're going down by 4, down by 4, down by 4. So this would be linear. How about over here? We go up by 1, up by 1, up by 1. How are we changing in the y direction? Plus 4, plus 4, plus 4. So that's pretty constant. So the rate of change would be 4/1, which is a constant rate of change. So this would be linear. And then how about this third one? Well, the change in the y, to go from 21 to 15, that's minus 6. To go from 15 to 10, that's minus 5. To go from 10 to 6, that's minus 4. And then up here in the x direction, we're going minus 1, minus 1, minus 1. So these numbers down here are dropping less and less each time as you go to the right. So this is becoming less steep. So it's not a constant rate of change. So then this would be nonlinear. So nonlinear. All right, so let's keep moving. How about if we just look at a graph? Well, is this a straight line? Not a straight line, so nonlinear. So when it says to explain, then just say not a straight line. And then try to write a little neater than I write sometimes. Not a straight line, okay? And that's all you'd have to write. How about this one? This would be linear, yes, because it is straight line. So you've got a straight line there. It's actually got a slope of 0, but still a straight line. Okay, let's move on. Try a couple more here. How about this one? Well, not straight, not straight. So not linear. So not linear. And when you explain it, the reason why it's not linear is it's just trying to get a little marker to work. So it's not, jump to an eraser, sorry. So it's not straight line, right? And that's how you tell. Not straight. Oh, got a new little tool and I keep bumping it. Okay, how about this last one, number 2? Well, that's a straight line, so that would make that linear because it is a straight line. So I don't know about you, but I think that's kind of easy. Pretty straightforward, right? What else could we see? Well, another way is to compare the equations. So you know if it's linear if you only have two variables, one or two variables, and you can't have any exponents on the variables other than one, and you can't have any variables in a denominator like that. So if we go through these and do a little dragging and dropping in, this first one would be nonlinear because you have an x or 2 in your exponent. The next one would be linear. The next one has because it has a x in the denominator of that fraction, that's nonlinear. And this one is not solved for y yet, but if I did solve it, it would be linear because you can put it in y equals mx plus b form. So that's how you do those types. Let's try a few more. So the first one, y equals x plus 5, that's in slope-intercept form. The exponent on x is only 1, so that's linear. This one hasn't been solved for y yet, but it would be linear if you did. This one does have an exponent of 2 on x, so that would make that nonlinear. This one has some parentheses. If you use the distributive property and got rid of it, then this would still be linear. This next one would be a straight line at y equals 4. And this particular problem, you're going to end up with a variable in the denominator, like you see right here. So that makes that nonlinear. So you have a worksheet where you do much of the same thing. So good luck on your worksheet and have fun.